Here we have a system where we have a small block on a frictionless horizontal surface that has a given mass. It's attached by a massless cord passing through a hole in the center. The block is revolving at a distance of 0.3 meters from the hole, and it has an angular velocity as it goes around that circular path. The cord is then pulled from below, so they're pulling downwards on that cord, and they're shortening the radius of the circular motion to 0.15 meters, about half the size. What is the new angular speed of the block? So in this case, the block is going around and around in a circle. It has kinetic energy. It has it has rotational kinetic energy, or a circuit for its represents circular motion. It has momentum and angular momentum. It's in motion, so it has all of these things happening. In this particular case, we are going to pull on the rope. We're applying a force to pull on the rope. That force is going to act as a tension through the rope, and we're going to end up pulling on the block by applying that same force. And we're going to pull the block inwards, so it's going to end up going about half the size of the circular path that it had before. And we want to find the new angular speed. And so here's the thing. If we are applying this force this way, and the block is going to tend to kind of spiral inwards to the new radius of motion, then we are doing work on the object. The work would be kind of difficult to find because the force would be changing as the radius of the circle changes. And so that would be pretty difficult for us to look at. But we know that the block is always going to be going tangentially to the circular path. And we know that the force that we're applying to this rope is always going to be radially inwards along the rope. So what we can say is that this force that we're applying is always perpendicular to the direction of motion. And what that tells us then is that the torque that we're applying to this block via this rope, that torque has to be zero because the force is acting right on the block, right on the center of mass. And the block is going to have angular momentum all the way around. So what we can say here is that if the torque is zero, the torque that we're applying, because we're applying that force right on the block, then that tells us that our change in angular momentum must be zero, and that must mean that the angular momentum at the beginning must equal the angular momentum at the end. In this case, we have a block. We can say that the moment of inertia of a single particle, in this case a small block, would be mr squared. And so our angular momentum at the beginning would be our moment of inertia at the beginning times our angular velocity at the beginning. And our angular momentum at the end would be our moment of inertia at the end times our angular velocity at the end. Our moment of inertia at the beginning is mr initial squared. And the moment of inertia at the end is going to be mr final squared. And we can see here we're given the mass of the block, but the mass isn't going to do anything for us. The original radius is 0.3 meters, and the original angular velocity is 1.75 radians per second. Those are all proper units already, so we don't need to change anything there. The final radius of motion is 0.15 meters, and we don't know our final angular velocity. But we can go ahead and calculate that. And we find that it's 7 angular velocity is going to be measured in radians per second. It's 7 radians per second, and it's going 4 times as fast. If it's got half the radial distance at the end, half the radial distance is 1/4 the moment of inertia. So if it's got 1/4 the moment of inertia, it's got to have 4 times the angular velocity so that it carries the same angular momentum at the end as the beginning, because there's no torque acting on it. There's no friction. The only force we're applying is right on a line through the center of the block. And so there's no torque. So the angular momentum is not changing. So the angular momentum at the beginning must be the same as at the end.